All right, ladies and gentlemen, today we're going to look at Unit 6, Thermochemistry, kind of get a little bit more into calorimetry and what that might entail, and some of the things that we can calculate from that. One of the last things that we didn't really talk about last part is some of the heats of the reaction. Now, where does that entail, or where does that look like when it's a part of the reaction? We can actually write those numbers as a part of the chemical equation. That might seem a little bit weird, and so we have different two parts. And so when we see the thermochemical equation, meaning the value is a part of the reaction, we do still balance out the chemicals, but it might sometimes require that to increase as well, depending on the amounts. Usually, again, tabulated values, so it's not too bad. Now, when we can notice that the 65.2 kilojoules is a part of the products of the reaction. Meaning, if it's a product, that means that the enthalpy or the heat is being given off as a product, meaning that when we look at it from an enthalpy point of view, it would have a negative value. And it's that negative value that then puts it there. Now, if we saw the energy on the reactant side, the delta H value would be positive if we needed to have that. How some of these values are calculated is known what is called calorimetry. We tend to use what is called a coffee cup calorimetry, and it's literally just that because we use styrofoam coffee cups. These styrofoam coffee cups that we can see here work great. They're fairly inexpensive. It's something that is used very widely in colleges because it still actually gets you fairly reasonable values with it needing to be done. And we have a number of these in our lab as well that we tend to use and will continue to use. So that's because, again, they're good insulators. We don't always have a cork top. Sometimes they will have a insulation top on on there as well, where it'll be just more styrofoam with a couple holes, one for the thermometer and one for your glass stirrer. Some of them get really fancy and have these little spinners on the bottom. We do not. We actually have to be careful and to make sure that our thermometer isn't all the way at the bottom, so that when we put our stirring rod in there, that when we stir, that we're not hitting the thermometer and breaking the thermometer. But this one is a little fancier one so that it would actually do that. And this actually gets you pretty good. Now we have a calorimetry, and this will allow us to calculate the energy flow. Here, the water that's inside acts as the surroundings. And so therefore what the reaction is going on will be also be able to measure. And that where that heat is going will go to the water, which we can measure a lot of times. What does this mean for us? Well, it gives us some values that we'll need to look at and calculate. And some of the parts is what's called specific heat. Now, the energy that is required to raise 1 gram of substance 1 degree Celsius or 1 Kelvin is the heat capacity, so better known as the specific heat. They are again tabulated values that we have here. Notice that we can see that nitrogen has a fairly high number for a gas, and some of the solids do a better job of dispensing that heat as opposed to retaining some of that heat. Now, water, as we can see, has a value of 4.18. That's going to be very important for us to look at and tabulate and remember, because that's going to be what we use in the lab fairly frequently as we do our calculations, because that will be the substance that we use as the surroundings to do that. So we might not be able to calculate the specific heat of an object or of hydrochloric acid or sodium hydroxide, but we can calculate and use the specific heat of water to see how much energy the water gained, because if the water is gaining energy, that means the other things are losing energy losing heat. And so we're able to kind of look at it from that perspective of what's doing what. As we look at, again, specific heat, you can calculate it out. I'm not a big fan of this equation. I usually like it spread out as into the values where you're actually calculating Q or heat. For that, you will find specific heat written in a couple of different ways, and that is C sub S. M is for mass, that's pretty common, and a delta T for your change in temperature, so your final minus your initial on there as well, as always. And so how much energy is it going to take to raise 1 gram of water 1 degree Celsius? Well, it requires 1 calorie, small c, or 4.184 joules to do that, to get it to raise 1 degree. And so what they use, and again, looking at liquid water, because water vapor has a different heat capacity to it as well. So there's a little bit of some of those things that we do have to be mindful of. Now this is the equation that I prefer to use, because after that it just becomes algebraic manipulation. And in this unit we calculate the Q, and are more interested in the Q than we are about specific heat. More specifically, a lot of times we're using water, so we might as well try to find out the heat that is being given off by water. So because the specific heat for water is well known, that's why we tend to use it. Again, using the coffee cup calorimetry to do that. And that's actually what we call it, a coffee cup calorimeter. So when we look at a problem simple as this, when a piece of iron that's at 356 kelvins is placed into water at 298 kelvins, what happens? We can do the basic calculations and say that, well, the temperature of the water is going to have to go up. We don't know by how much, but it will find itself to normalize. And we know it's going to go up because the iron, even if I take this little piece of iron here and I put it in water, we should know that it is going to increase the temperature of it, because we've seen, and hopefully you've seen that happen, like you put hot water into cooler water, the temperature of even that will go up. Now, by how much, it depends on some other factors that we're not going to worry about right at this moment in time. But the temperature is going to go up. The temperature of the water is going to go up. The temperature of the iron is going to go down. So T of H2O is going to go up, and then the T of the iron is going to go down. To what degree? We could worry about that at a later time. So here's another little problem that we can look at as an example of how to actually calculate specific heat. And that is utilizing what we know. If we take and add things to what we have, I like to write it out as showing our equation. Q is equal to mass times C sub S times my delta T, which delta T is, again, temperature of my final minus temperature of my initial. Here I can look at it and go, okay, my Q is 435 joules, and that's equal to 3.4 grams of olive oil. And if you remember from your Popeye cartoons, she is pretty skinny, so 3.4 grams might not be too far off. Pause for comedic effect. We don't know what the specific heat is. we do know what the temperature changes are. It started at 21 and finished at 85. We can do that that basic subtraction to give us a value of which looks to be 64. So I'll just do the erasing to give 64. And then here, because it says degrees Celsius, we should be okay. So now we can do this a couple of different ways. We can do our multiplication, or we can do our division as we maybe need to. With that happening, we can then put our 4.35 joules. We will then divide that by, I'll put it in parentheses, 3.4 grams times 64 degrees Celsius. And that is going to, again, equal our specific heat. If I do my calculations here, I will find that I have 4.35 divided by 64 and I will get a value, and a fairly low value, of about 0.0019, and that would be joules per grams times degrees Celsius, and that will give me my specific heat for the olive oil at this time. Now, I've kind of mentioned this a couple times in the notes already and throughout class, is that a lot of times what we're looking at is where is this going? Now, the heat of the surroundings is the negative of what the system is doing, is really what we're looking at with this equation here, in that if the system, and maybe writing it out might be best, is that if this Q of the surroundings, or the energy of the surroundings, goes up, that means the Q of the system needs to go down. Now, if the Q of the surroundings goes down, that means the Q of the system goes up. So there's an inverse part to it. So as one goes up, the other one has to go down. Usually what we see is that the surroundings, water, is going to gain some heat, and therefore that means that the system is losing the heat. Now, the amount that the surroundings goes up is the same that the system goes down. And it's the same for the other way. If the surroundings heat goes down by a value, that's the same amount of energy that the system goes up with that. And so that's kind of what we're looking at from a more mathematical point of view with this equation at the bottom. So if we just have a conceptual understanding of it, we should be able to understand kind of what we're looking at with that. In the next video, we'll look at kind of more applications of this as well, but we should be ready to get into the lab and do some specific heat calculations.